As we think more about how we would analyze the performance of code, it's important to be able to take a larger portion of code and identify what parts of it have the greatest impact on the performance, meaning which parts of it will take the longest under certain conditions. So here's a piece of code in which there's a variable x set up using some math, a variable y set up using some math, some print statements, and then a loop from I equals 0 to an array length, printing out information. So the question that I would ask you is, which portion of this code will have more impact on the total operation count for that code when the array has one element? And then, which portion of the code will have more impact on the total operation count when the array has 100 elements? You can see I've split it into two portions here, the blue portion down below and the pink portion up above. So which of those will have the most impact and under what conditions? So pause for a moment and think about which one will have the most impact, when will that change, what are the conditions, why does one portion have more or less impact? So pause the video and think for a moment about that. If we count the number of operations, this is our constant portion of the code here that will always have the same number of operations no matter how many items are in the array, at least one, so that we don't get an error here. We've got a multiplication, a subtraction, and an assignment. That's 3 operations on this line. 3 more operations on this line gives us 6. And then there's possibly 2 here, combining some stuff into a string and printing it. So that's 8. And then combining some stuff and printing it, that's 10. So if there's one array element, then this will have 10 steps. If there are 100 array elements, this will have 10 steps to do. It doesn't really matter. It's only looking at the first item in the array. But on the other hand, the loop down here will do an assignment and a comparison to decide if the loop should enter. Then it will do the body of the loop, the print, so that's 3 right there. Then it will possibly increment the counter there if the loop was allowed to enter. And it will then test the condition again and possibly enter the loop again. For one item or one element in the array, we'll have the assignment, the comparison, the print will happen because 0 is less than 1, the array's length, which means the increment will also happen. So that's 1, 2, 3, 4. And then it will do the comparison, 5, but the comparison will fail. 1 is not less than 1, and so our loop will be done. So that will take 1, 2, 3, 4, 5 operations. So let's start to think about this a little more clearly. We have the portion of the code. We have the size of the array. So we'll call this part 1, and we'll call this other part 2. And we'll say we know part 1 is 10, no matter what the size of the array is. So if the array has 1 item, the array has 100 items, it will take 10 steps in that portion of the code. You don't even have to tell me how big the array is as long as it's more than 1. So if it was 5, if it was 10, etc., I know this portion of the code will take 10 steps because it's only looking at the first element. This portion of the code will take a variable number of steps. It takes 5 when there's 1 element in the array. It would, if there were 5 elements in the array, it would do the equals only once, but then all of the other parts would get executed at least 5, sometimes 6 times. The comparison will get done 6 times. So we've got 1 for this, 5 increments, so that's 6 there. This will happen 6 times if we include the time when the comparison fails. So that's 12. And then the inner part of the loop will happen 5 times, once for each array element. So that's 17. So we'll take 17. And if we have 10 items, well, there's the 2 that are going to always happen, setting I equal to 0 and the comparison that fails. And then there will be 10 for the plus plus and 10 for the print. That's 20, so 22. And if we have 100 items, then we'll do the print and the plus plus 100 times. We'll do, this should be 32 because this happens also for each time that passes as well. So there will be 1 assignment, 1 comparison that fails, that's our 2, 10 comparisons that succeed, 10 times of incrementing, and 10 prints, so that gives us 32. Now for 100, there will be 100 comparisons that succeed, 100 increments, and 100 prints, 1 assignment, 1 comparison that fails, 302. So you can see that this one is growing pretty quickly. In fact, it's linear. It's 3 times the size of the data plus 2, those 2 that will always have to happen, assigning and failing sometime to exit the for loop. Now, if I add an extra column to this for the whole thing, we can just add the parts here. 10 and 5 gives us 15 steps that are needed for when there's 1 item in the array. 10 and 17 gives us 27. 10 and 32 gives us 42. And 10 and 302 gives us 312. Now, the interesting thing to note here is that the pattern for the whole thing will follow the same general behavior as the pattern for the part that grows the fastest. So this 10 starts to become pretty insignificant in the overall performance when the for loop starts to have to execute more and more because the data grows. So we say that this portion of the code dominates in terms of performance. It takes so much time that the other portion of the code doesn't really matter. And the reason that it does so is because this is constant in its performance. It never grows. But this one is linear, as we mentioned before. It's 3 times the array size plus 2. So it's linear in the size of the array. And so that means that the overall code is going to also be linear. It's actually going to be 3 times the array size plus 12. The 10 for our constant portion here, and the 2 for the I equals 0 and the comparison that fails. So what we tend to do in computer science when we're doing analysis of a larger portion of code is we tend to throw away the parts that don't dominate. We tend to focus on the parts that will grow quickly because these are the parts of the code that will cause delays for your users. And so what we will do is we will use a thing called big O notation, where we would say O of something, and we'll usually use N in relation to the data size of the array we're dealing with, or the string that we're using characters from, or whatever data we're operating on here. So for instance, our constant portion there we can refer to as O of 1. Our linear portion here we could refer to as O of n, because it's going to be something times n. We will sometimes see things that are O of logarithm of n, which actually is a little smaller than linear, so we should put it here. We'll call that logarithmic behavior. We will see sometimes things that are O of n squared. And we'll call those quadratic behavior, a term you may remember from math classes before. And so in computer science, we tend to pay attention to the category that something belongs to, because that's how it's going to grow as the amount of data grows. And we see many examples of data that just grows and grows and grows in terms of the number of grades you accumulate over your academic career, or the number of students who have ever enrolled at UNH, or various things like that. So if we have an equation for a piece of code, the operation count for a piece of code, like we did here, we had that our operations were equal to 3 times n, the size of our data, plus 12. Right? We had 300 plus the 10 for this constant portion, and the 2 for the I equals 0 and the failed comparison. When we are categorizing for big O notation, what we do is we pay attention only to the fastest growing portion. This is usually expressed as the highest power of n. And we'll see some examples where it's n squared plus something n. Well, we would pay attention to the n squared portion. If it was log n plus 12, we would pay attention to the log n, because logarithm grows faster than a constant, and so on. So this is similar to your math classes where you talked about degree of a function. What grows the fastest? What's the biggest power in there? Here it's n, or in other words, n to the 1 is the highest power. We also ignore any coefficients, meaning here we would ignore the 3 times, because what we really care about is putting it into one of these categories to see how fast it grows. And so we would care that this one is linear. It's going to form some line that angles upwards, which is growing faster than a constant, which is just a flat line, or growing faster than a logarithm, which is sort of like a slowly growing hill. So we ignore all those coefficients, meaning that this 3n plus 12, we would categorize as just O of n. It's linear. It grows in some linear fashion. It's got this little constant amount added on. We don't really care. And it's got this little 3 times part happening here. If we found that we had 2 linear pieces of code, then yes, we might look at what their multiples are, or what their constant portions are, or stuff like that. But if we're choosing between something that's, say, linear versus something that's constant, we want to choose the thing that's constant, because our users don't want to wait, and we want to get answers in a reasonable amount of time to the questions that our code is working on. And so we will choose the slower growing category of algorithm anywhere we can. And if we identify that there is some fast growing portion of our code, we might focus our attention on optimizing that portion of our code. So this is a useful tool that you're going to practice while looking at models B and C from the activity, that will allow you to find the portions of your code that might be slowing a program down, or to choose the approach to solving a problem that is in the faster category and therefore is going to do well as the amount of data that you deal with grows and grows.